Welcome to the last lesson in Chapter 7. Here we're looking at double angle identities. And to see the connection between double angle identities and the sum identities, I would like you to work through these warm-up questions. So notice sine of alpha, well, sine of 2 alpha would be the same as sine of alpha plus alpha. So use the sum identity for sine and see what you get. Simplify that down. Similarly, tangent of 2 alpha will be the tangent of alpha plus alpha. Again, use that sum identity for tangent. Simplify that expression to see what you get. And the same idea for cosine of 2 alpha. Pause the video and try those questions. Hopefully this is what you got for question number 1. The sine of 2 alpha is equal to 2 times the sine of alpha cos of alpha. And for tangent, here's what you get. 2 tan alpha all over 1 minus tan squared alpha. And then we'll look at cosine. And when we use that sum identity for cosine, we'll get cos squared alpha minus sine squared alpha. Now, if you looked at your formula sheet at all, you'll have seen that there are two other identities given for cosine of 2 alpha. And those come from using the Pythagorean identity to do some manipulating. So here, for example, if I was to replace sine squared alpha with 1 minus cos squared alpha, again using that Pythagorean identity, it would simplify down to what we have in the box here, 2 cos squared alpha minus 1. Similarly, if I had replaced this cos squared alpha with a 1 minus sine squared alpha, it would simplify down to what's in the red box here. And so we have three different identities we can use for a double angle of cosine function. Well, here let's look at an example, how we might make use of these identities. We're given an angle theta. In standard position, terminal arm is in quadrant 4, and we know the cosine of theta is 2/5. We're asked to determine the exact value, first of all, in number 4, of sine 2 theta. So we'll start by thinking about the identity. Sine of 2 theta is equal to 2 sine theta cos theta. Well, I already know cos theta, but I don't know sine theta, so I need to figure that out. So again, like we did with the sum and difference identities, I'm going to sketch the angle theta in standard position and fill in the length of the sides for x and r and y I need to calculate. That is, I need to calculate the value of y. And Pythagorean's theorem will help me with that. Y squared will be 5 squared minus 2 squared. And we'll get a y value of square root of 21. I take note that it's in the fourth quadrant, so I'm going to take the negative square root. So you can see that here in this. It's just a little bit hard to see, but there's the negative sign. And then I can substitute in y being negative root 21 all over the r value of 5. That's going to be the sine of theta. Simplify it, and there's our answer. Question number 5 is similar, but I have some more options. So I have the double angle for cosine, and I know the value of cosine theta. So as I look back at the three identities that I have up here, this first one has a cosine and a sine. The second one only has cosines, and the third one only has sines. So this second one will be the most useful or the easiest for me to get the answer. So I'm going to use that identity. 2 cosine squared theta minus 1 is equal to cosine of 2 theta. And then I can just plug in the value that I was given at the beginning, where cosine theta is 2/5. So I'll have 2/5 being squared. So remember This squared says all of cosine theta is being squared. So the 2/5 is squared, and I changed this 1 to a 25/25 because I looked ahead and thought, oh, when I square this fraction, I'm going to get a 25 in the denominator. Then when I subtract the numerators, I'll get negative 17/25. Pause the video if you need to write this down, but I will continue on to the next question. These next two questions are similar to what we did in 7.5 with the sum and difference identities. And so we look at this first expression and we see cos squared something minus sine squared something. Oh yeah, that's going to be a double angle identity for cosine, where the alpha, in this case, is a pi by 4. So this is cosine of 2 times pi by 4, which when we simplify down will just give us cosine of pi by 2, which is 0. The end of question 6. Pause if you need to, but I'll go on to number 7. Now as I look at this identity, it looks close, but a little bit different. Here's the double angle identity for tangent, and it's close. My numerator, I have 2 tangent of an angle, but in the denominator here I have the tangent squared of the angle minus 1, whereas here I have 1 minus the tangent squared. So I'm going to have to do a little bit of manipulating in order to get it into the form that I want it to have. So here's what I did. I factored a negative 1 out from this denominator. When I factor the negative 1 out, this 1 became positive, and so it used to be negative over here, and the tangent becomes negative. It used to be positive. So when I factored out the negative, the sign switched on both of those. So now what I've written in blue here looks identical to what I have in my identity. So I can make use of the identity from here with that negative 1 in the denominator. Let's get this out of the way now. So now I've taken the negative out in front here. So I have the negative of this expression, which is just the negative of tangent 2 times pi by 6, which is the negative of tangent pi by 3. Tangent of pi by 3 is root 3, and so my answer will be the negative square root of 3. A bit of manipulating involved, but again, just making use of the identity for tangent 2 theta. Pause the video as you need, but I will go on to number 8. Again, we're going to prove an identity. Whenever we have an identity with a situation where on the left side, or on one of the sides, I have cotangent of just an angle, theta, and on, well, somewhere else in it, I have 2 thetas, I want to replace these trig functions with the double angle with their identity, so that I'll only have thetas, not 2 thetas, inside my trig functions. So that will be my first step. But I don't always know exactly how to start with cosine, because cosine of 2 theta, I have 3 options. Before I get into that, I only had one option for the sine of 2 theta. So sine of 2 theta is 2 sine theta cos theta. At this point, I'm going to pause and think for a moment. I look at my left-hand side. I see I have a cos theta over a sine theta. On the right side, I have a sine theta in the denominator. Well, I like having this sine theta here and this sine theta here because so far those two I want to keep in the denominator. So this cos theta and this 2 I want to be able to get rid of somehow. So that's a clue to me that the identity that will be possibly the most useful for this cosine 2 theta is the double angle that only has cosines in it. So that's what I've tried here. Now, if I use the other identities, am I stuck and I'll never prove the identity? Nope, we'll get there. It's just this is likely to get me there faster. So making some smart decision making as I look ahead and as I compare numerators and denominators on both sides of the identity. So this time I'm doing this as a two-column proof. So I just drew the line down from the equal sign, and rather than putting equal signs in between each line. Well, as you can see as you've looked ahead, on the right-hand side, I have this -1 plus 1 that cancel out to give me 0. And then I just wrote this cosine squared theta as a cosine theta times cosine theta. Would I have to? No, but again with the proof, I want to be really obvious in my steps. So I chose to make it really obvious. And then I can see that in the numerator and denominator, the 2's will cancel, and one of the cosines will cancel, and I just get cosine theta over sine theta, left side equals right side. If you do a two-column proof like this, where I don't keep writing everything down on one side of it, I do want to make sure that I say left side equals right side at the very end, once I've shown that the two sides are identical. Pause the video if you need, but I'll go on to the next page. And let me pause it here and give you some time to try this proof. See what you can do with this question. When you're ready, restart the video, and I'll show how the proof goes. Well, at least one strategy for doing the proof. I'm going to do a two-column proof again, so I put that vertical line down along the equal sign. On the right-hand side, I have sine thetas. On the left side, I have cotangent and cosecant, so I'm going to rewrite these in terms of sine. This double angle in the cosecant I don't have a rule for, so I'm going to rewrite that in terms of sine. There we go. As in the previous proof, because here I have a double angle at 2 theta, I want to use an identity here to rewrite this with just a trig function in theta and not a 2 theta. So that will give me a 2 sine theta cos theta on the right rational expression. And now because I'm multiplying here, anything in the numerator, any factor in the numerator that is, that cos will be multiplied to this 1, can cancel out with any factor in the denominator, and the cos theta is multiplied to the sine theta, to the 2, to the sine theta, so they're all factors, which will give me my next line, where I can see that I've shown that the left side is equal to the right side. Goofy stuff happening here. And there we have it. The proof is done. And that's the end of the lesson and the chapter. So there you have it. And at the bottom of the page, you can see some questions to practice. There'll be time in class to work on this now that we're kind of flipping this classroom. All right. Happy practicing.